So we are here. All right, so now we're down to vulnerability discovery, which we've only talked a little bit about fuzzing here in a simple way, and we can talk a little bit more about it. It is not a very mature field. Last time I taught this class, Ben got real excited about the Carnegie Mellon tool. I forget the name of it. Carnegie Mellon has a tool that fuzzes Windows applications, and he ran it for months and didn't really find anything that we could use. But anyway, this is actually a very old trick. It's been done for hardware. And if you look at Amazon and other cloud services, they have a tool called Chaos Monkey. Netflix and Amazon both use it, Netflix, where it turns off things that should be working during a business day. It turns off a server, it breaks a service, it breaks a network connection. At first, this sounds insane, but the point of it is all the engineers at the company have to prepare to handle faults. And they're serious about it, so they want your app. If you put an app that has like a login, you should have some code that says, what if the server is down? Have another server or something. And in order to make sure everybody always does that, they do randomly turn stuff off all day long every day. So the end result is everything is much more resilient because, of course, that's the way real servers are. Even if you're not deliberately turning them off, components are failing all the time. And so anyway, that's one thing, to just have fault tolerance so that when individual services go down, you have backups. But in our case, we're looking for flaws in the device where a fault has an unexpected result. And I think you can inject electrical signals into electrical devices, and that is, I think, how this all started. There was there were some people doing command line bash code over a modem in a thunderstorm. And the thunderstorm lightning caused the modem to drop bits, and they started getting weird things out of the programs, and they realized that sending random data to a program was actually a pretty important thing to do, and they found a bunch of bugs in the Linux commands that they were using at that time, and realized people should be testing things this way all along with fault injection. So you can send in random things, you can send in carefully arranged faults, and you can do reverse engineering, where you look at the source code and try to guess what the bugs are. So here's the ideas here. They're talking about how to design a system to do this. So you generate network traffic by doing normal work with a client package talking to some server. Then you use a sniffer and capture that traffic. Now you choose some way to modify that traffic. Now, if you're really dumb, you'll just flip random bits in it or make fields longer. But if you get clever, you might want to choose more careful changes so that you waste less time on obviously invalid input that will fail the first tests, and you put in input that's more likely to penetrate deeply into the app. Then you inject this damaged traffic to the server, and you monitor the server to see if it crashes or does something else interesting. Usually you're just running it in a debugger and observing its crashes. It was Failure Observation Engine. That's the Carnegie Mellon product that Ben ran in the lab for a long time trying to find 0 days and things. And the problem is he found a lot of faults, but we were not able to exploit any of those faults. So it might be that the observation engine was okay, and our skills at developing exploits after the fact were not as good. But somehow he didn't actually discover anything exciting and new with it, but it might be worth another try. The logical thing to do if you want to find interesting bugs is to look for the parts of the application that are strange and almost never used, because those are probably not really tested and they're probably not really updated. And this is where a lot of examples of this, the one that hit the news about 1.5 years ago was a failure in Zen, which is the hypervisor used by most cloud services. And every virtual machine on a Zen hypervisor has a virtual floppy disk, which everyone had forgotten about and nobody looked at, and that had something simple like a buffer overflow where you can take over the device. Been there for years, nobody noticed. That's usually how it goes, because the corner part of the code that is not in use, nobody tests it, nobody cares. All right, and here's an example of this. This is an IIS web server has some strange thing called an IDA file that is almost never used, and it turned out to have interesting vulnerabilities, of course, because nobody was testing it. So the most perfect way probably to make code is to manually make a bunch of fake code, modify it with a smart human. Automated generation is, of course, a lot faster, but less precise, and you kind of blend the two. So you can do a live capture where you inject faults directly into live network traffic, where you put something like a proxy and you modify as it goes by. And I mentioned the fuzz generation is just random data injection, where basically I think lightning storms on modems cause just randomly flipped bits. And that's the simplest kind of automated fault generation, just flip bits in the input. So open source apps, lets you do a fancier job of this. There's a thing called American Fuzzy Lop where you add code to the product, recompile it, and now that code helps you analyze the crashes, which you can see would be awesome. You know where it crashed more. But that'll only work if you have open source code where you can modify it and recompile. Yeah?
Is fuzzing with Unicode values and things like that?
Fuzzing with what? Oh, Unicode, yeah?
Unicode stuff, is that, does anybody do that?
I haven't heard that particular, but I'm sure that's an option. I mean, certainly using other languages, and Unicode is obviously a good thing to try. I haven't heard of any famous results found that way, but it certainly sounds good. I know the main use of Unicode I know is to bypass filters. But I would think, therefore, you might very well find faults because the developer forgot to think about that and put in various conditions that only work if you have 8-bit characters. It's a good idea. Anyway, so if you have closed source apps, you can modify the data, but you can't modify the code, and therefore you have to do a black box approach where you feed in stuff and you don't know what happens and you try to determine whether it's crashed or not. So if you're trying to find buffer overflows, then what you want to do is make elements longer, trying to exceed the buffer and make it crash. So one logical way to do this in a sort of automated fashion to avoid wasting too much time is this logic. You take the strings that are going in, like a web server, and you find the delimiters, like spaces and slashes and carriage returns and tabs, and you break everything up by delimiters into fields, and then you just make the fields longer. So instead of putting in more spaces between the get, you figure one space probably delimits it, you make the individual pieces longer, and so you'll get things like this. You choose something to inject. He chose to inject EI 2003, so you inject that in the first field, inject it in the second field, third field, fourth field, and each one of these fields has the extra characters put in it. And this makes a set of attack strings that is not too large and that is likely to find a problem if there is a problem there. Although I would think if I was doing it, I would want to add something like 500 A's in there to make it really long, but you try various options. Here's another one. If you have input sanitization, for example, there's one here where you had 1.1, and I don't see it, but it seems to me like logically at some point he's going to put this EI in the 1.1, and I think this is it. And it might be that it knows enough not to take letters in a numerical field. So you might find that you're injecting stuff and it won't do you any good. So if you want to get past delimiters, instead of injecting something alien, you just repeat the characters you have. You know a T is okay in the get, so you put in more T's. You know a 1 is okay in the number, so you put in more 1s. This is more likely to actually penetrate the first stage of filtering and get deeper into the code where you might have things like buffer overflows. All right, so now you've got to make a network connection to the target app, send your modified stuff, and then measure to see if it crashes. The nicest explanation of this I saw was Dave Kennedy, who found a 0-day in the Apple MacBook Pro wireless card. It was one of the first major vulnerabilities in Apple, maybe 8 years ago at DEF CON, and he had a simple system with, I think, 3 computers. He'd have the target, which is a Mac. He'd have another computer sending random packets to it, and he had, I think he had 3 or 4 computers. He had one sending packets to it. He had one just sniffing the wireless network and recording all the traffic, and another one sending a ping to the Mac every 10 seconds to see if it was dead yet. And so he let this run all night. Get up in the morning, the Mac is dead. So he goes back and finds which ping stopped, and then the recording of what packets were there, and then he runs that last 10 seconds slower to find out which one packet caused the crash. And that's how he found the 0-day. And he showed a video of this happening and explained it at DEF CON, but he didn't do it live because he said he didn't want anybody running sniffer in the audience and finding the attack, because he told Apple he wanted them to fix it. And when he told Apple, Apple said that he was lying, he had modified the hardware, he was completely fake, he should be drummed out of the community, and it's just a coincidence the next month they patched the driver. And that was the bad Apple. About 8 years ago, they were where Microsoft was 15 years ago, where they just shoot the messenger, lie about their product, conceal their flaws, and expect to continue selling products on that basis. But after they delayed a PDF update, and there was a real spreading virus on the Mac, they spent 6 weeks telling their help desk to lie about it, and they were so humiliated when someone leaked it from inside Apple, which will really get you fired. Apple takes leaks more seriously than the NSA. They couldn't lie about it anymore, so they had to actually admit they have flaws and they have patches, and they're no different than everybody else in that regard. And now they're not that mean to researchers anymore. They no longer have a management that pretends they have no flaws. Yeah?
By what means did they say that he was lying? Was it an official, like?
Yeah, their
press
official
release?
statement on this vulnerability. Apple normally does not discuss security things at all, but they did release a statement saying this so-called attack is all fake, this guy's lying. And it was just because he had a real reputation in the community, and the vulnerability researchers were aware that this is what you normally get. If you go to a company and tell them about a vulnerability, you get the same treatment as someone going to the Pope and telling him that the priests are doing bad things to little kids. They just figure shooting you will solve the problem. Because it's far too much bother to actually admit there's a gigantic problem and a lot of money has to be spent to fix it. It's always that way. Anyway, one issue that will get you here if you're using network traffic is the Nagel algorithm, which tries to slow down small packets so they can be grouped together. And you don't want that happening when you're deliberately sending packets of different sizes and you want to know what they do. You're not actually trying to deliver that data to the other end in the most efficient way. You're trying to make sure this goes now and this goes later, so you have to disable that with a flag in the operating system. All right, and then there's fault monitoring. How are you going to know when the app fails? The simplest thing, of course, if you're interactively doing it, is run it in a debugger the way we do, with something like immunity, and then when it crashes, it stops and pops up an error message saying access violation at this address or something, and then you know. The access violation exceptions are the ones you want most because those suggest that you have somehow tricked it into trying to go to the wrong address, and if you're lucky, that's an address you can control, like the EIP or the EBP or something, and that's going to be likely that you can take over the machine. All right, and that's all there is in that chapter. Not what I wanted to cover, but it gives you a general structure here, and fuzzing is more about how to really do this. So you can do static analysis, where you look through the code and you could, for example, quite easily even just grep and find like format string vulnerabilities. Find printf statements that don't have a comma between the parentheses. Then they apparently don't have format comma data. And then you could pretty easily find simple kinds of vulnerabilities like that, find a statement in C that uses the string copy function but doesn't have an if before it to check for length. That's pretty likely to have a buffer overflow. You can see certain patterns like this will obviously be suspicious spots. And when I first taught the hacking class years ago, one guy that came was actually said he was the champion on some Black Hat forum at finding 0 days. And this is how he did it. He just looked at source code and he could spot certain patterns and find 0 days in open source applications. So that's one option. The problem here is if you do this, you'll find some, say, format string missing in a print statement, but what's actually printed didn't come from the user anyway. It was some internal system message, so it really doesn't, it's technically an error, but it's not actually exploitable. And you won't easily tell that from a source code review. That's the problem. That's why fuzzing is nicer, because you will only find things that depend on the input. But both of them have their purpose. But in one sense, fuzzing is scalable. If you make a network fuzzer that speaks a common protocol like SMTP, you can clearly use it for any SMTP server. And there was a commercial fuzzer I got to use at one of the B-sides in San Francisco. I had the iPad Mini, which was brand new then, and I brought it in, and this guy had a vendor was there with a commercial tool he wanted to sell, and I said, well, let's see it go. I turned it on, and within like 5 minutes, it found a 0 day and crashed my iPad in Bluetooth, because the Bluetooth stack was, of course, new, untested, and I was writing it up, taking screenshots, and putting it on Twitter when he stopped me. He said, oh, no, you can't tell anybody. I said, dude, I can't tell anybody. He said, oh yeah, because this might offend Apple and Apple might punish our company. I need to ask my boss for permission to tell somebody. So of course, nothing ever came out. Because if you ask authority figures for permission, they will always just be timid and say, oh no, don't do anything that might like rock the boat or take a risk. But I don't know how they expect to sell their products if they won't brag about what their product does. But anyway, there are commercial products out there. But anyway, you can write your own too. Simple strings might work, just sending long things like .. 500 times or 5,000 times. That will try to move to other directories. And if any part of it is vulnerable to directory traversal, then it'll crash or have some unexpected result. Some parts of the code won't be hit by a fuzzer though. For example, you might have like a CAPTCHA or some other part of the code that requires certain input that you can't generate. And you can't get past that with your fuzzer. So also if you try to change too many parameters, then if you change one parameter and have 10 values, there's 10. If you have 2, 3, 4 parameters, you have 100, 1,000, 10,000. Pretty soon you've got an awful lot of cases to where it's taking too long to fuzz them all. This is why Microsoft resisted it until after they put out Vista, because they said fuzzing is a random process and you never know when it's done. That's like sloppy and unprofessional. We prefer source code audits and things where you know what you're doing and you know when it's done. And it wasn't until they were humiliated by Laurent Gaffey twice, who found 0 days in Vista after what he called 10 seconds of fuzzing, that he convinced Microsoft that they need to knock it off and do some amount of fuzzing. You don't know how much is enough, but you should do something like 24 hours of fuzzing before you send out a product, so at least there isn't something in there that can easily be found by your attacker with a fuzzer. So that's the game. So these are different ways to find bugs, and they're all different. Fuzzing will find some, static code analysis will find some, dynamic analysis will find some, and you just do whatever you can. And there are two philosophies. One is that these different techniques will all result in finding all the bugs, and I think nobody is dumb enough to believe that. But the other way to look at it is, these are all the tools the bad guys have too. So if you find the things you can find with these tools, then it's going to be harder for the bad guys to find it. They will have to somehow develop a new tool, so you ought to reproduce the steps that the bad guys are going to do anyway, and then you'll hopefully find the bugs that they would find. So Spike is an example of a good fuzzer, pretty easy to use, and you've got a project to do it, so I'll point you to this. This thing creates network traffic, and if you try to make your own network traffic, the really irritating part is the CRC32 checksum at the Ethernet level, and there are checksums at higher levels of the protocol, and that part is just annoying. That's why I like Scapy. Scapy automatically calculates that, and so does Spike. So you can just change the payload, and it will automatically create valid network traffic delivering that payload, because you're probably not expecting to find a bug in the TCP handshake. That's deep in the OS, and most of the time we're fuzzing an application. We're not expecting to find bugs in the OS. That's another issue. So Spike has functions you can put in your configuration file. You can send a string, and it will just send that literal string. You can send a variable, and it will then send a series of inputs there. The first one will be message, and then it will put in random things. And you can read a message from the server here, if you have to read something and then respond. So here's enough to fuzz vulnerable server. You read a line, which is the prompt saying, hello, welcome to the vulnerable server. Then you send trun, and you put a random command after it. And trun, remember, is the one we're exploiting in quite a few of these projects. That's enough, and it's pretty good fun. If you run that thing, you can catch it in Wireshark, so let me bring it up here. I should be able to do it if I was a little more efficient. I'd have these things already started, but that's all right. We'll cope. All right. So let's get vulnerable server going. I think it's all set. In fact, it's even running. I might be able to do it right now. That's the exploit in the previous attack working. Let's get out of here. All right. And get out of here. Okay. And so make it a little bigger. And cat SEH8. And this will give me the IP address and all that jazz to connect to the server. So let me just bring up the Spike project, which is right here. All right, the last project, last required project. So first you have to connect to this thing, and this is the simplest command. So generic send, execute this command, IP address, okay. This will send to TCP, and it will use a config file. So first you have to make the config file. Let me get this junk out of my way. All right. So first I'll make this thing, simple.spk, which will contain that. Okay. A Spike file. Oh, it's already there. Good. All right. And now I have to do this. Let me see if I have the right IP address for my Windows server. 172.16. No, that's not right. That's the client. All right. Let's have my IP configure. So this thing is 1.173. Okay. So this is the command that runs Spike, and it picks the parameters from that file. So it's going to send stuff here on port 9000, and that 129 should be 173. So that should do some fuzzing, and we can see the results. Oops, not that one, this one. All right. And oops, I want to be in this window. Okay. All right, 173 is this number. Let's see how it looks. All right. And couldn't connect to the target, so I think I've done something wrong. Just a moment. Okay, 172.16, 173. Oh, I'm not running the Vuln server. Haha. All right, let's run the Vuln server. All right. And since I'm going here, let's run it inside immunity, so it won't just crash, but we can see the nature of the crash. Might as well do that. That's more enlightening. So immunity and file. Here's Vuln server and run. So we're set up as usual. And now I should be able to do this. And there it goes. Nope, couldn't connect to the target still. So let's see, 172.16.1173, just a moment. That's what I've been feeding in. 173, I forgot to change it. That'll do it. Nope, still can't connect to target. All right, netcat 172.16.1173, right? You guys see my mistake? 9,000. Oh, it's 9999. Oh, that'll do it. Thank you. Oh, good. Thank you. Good. So then all I have to do is this one and make it 9999. All right. All right. There we go. So now it's sending stuff up to the server. And if you look at the server, you'll be able to see what it's doing. Let's just stop this and go here. And there it is, running through lots of stuff. If you look at this window, it shows you all the connections coming in and closing. It's just sending hello world over and over and over. I send a fixed string, so it's pretty boring. Not going to find anything exciting with this. So let's move on to the next one. That just sends hello world over and over. So here's the one that's going to do variables, starting with hello world. So simple2.spk is here. All right, I don't have it, but I'll put it in. Here's what sends variable. All right. And if I execute that thing again with simple2.spk, it should be more interesting. And I gotta put there. All right, there it goes. And if I go over to the Windows machine, it should already be dead, or it should die pretty soon. I may have to use something a little smarter, but notice how it's sending large things, and I would expect it to crash, but it hasn't died yet. And if you look at it in Wireshark, you can see that stuff go by. All right, so you'll see these messages, and you'll see them go by in this window here. If I stop this and go back, you should be able to see what's coming through. I'm not having any luck scrolling for some reason. Here we go. Those are just showing the closing connections. But anyway, all right. But you should see a lot of those things going through. And if you use a more sophisticated command, I think that's the problem. It's sending hello world. It's not sending valid commands like trun and stuff to the server. So it's all just being ignored by the server. So here, let's try this one, which is better. This is the one we're actually been exploiting in quite a few of the projects. The trun, followed by thousands of characters, will cause buffer overflows and SEH vulnerabilities and other fun ones to attack. So let's make that one, which is trun.spk. Okay, now, see if I have it. ls, I say. It's not listening to me. I'm in the wrong window. All right. I don't have it. All right. I do have it. All right, good. And so now let me get my Windows machine is up and running. It looks like it still is. I'll just leave it go then. So I should be able to run this mess with trun.spk. And the Windows machine is indeed dead, exception. It should die within just a few seconds, because that's what you did before. You'd send trun followed by some characters, and it isn't too hard to reach the point where it crashes. So it will only take a few commands to see it crash. All right, and that's the game there, and you can play with other versions of it here. And here's another fuzzer. You can run it again and stop it and see the traffic in Wireshark. You can follow it, and you'll see it's pretty simple. There's the trun, and here's the next one, just sending a whole bunch of A's and so on. It's sending all these packets, and what you can tell is that the ones that don't crash it end up with trun complete, and it's ready for the next one. When you crash it, it just gives you, welcome to vulnerable server, trun complete is not there. So that means that's the one that crashed it, and now you know that this thing, 5,060 bytes of that junk, will cause it to crash. So this is how you can find them, and you can find a variety of these things. Here's another one that'll have a whole bunch of dots and characters hit it. That's a simple tool to create valid network traffic in patterns you can specify, and it's good enough to fuzz simple simple programs like that. All right. And so there's a more complicated spike script that will actually send more complicated things like binary things, half word, big ending, message. You know, it understands all the variable types like Scapy, and you can send all sorts of complicated data structures over the network to match whatever the server expects. And if you're clever enough about it, you know, you have a high chance of finding interesting vulnerabilities. All right. So I got a few iClicker questions. And as I said, that's all I got. Not as long as usual today. I don't see Tom, so I guess we're not going to hear more about that jailbreak today. It'll be in a future class, but it's pretty awesome. So let's have the iClicker software. And in lieu of that, I might show you this target thing, which I'm pretty happy about. Although it's not at the binary level, it's at layer 7, but it's still pretty fun. All right, so let's see if I can get this thing to fit in the screen better. Okay, which process do you have to disable for effective fuzzing? All right, I guess I'll quit at 35. That's the Nagel algorithm that sends packets out of order for efficiency, and that is not what you want when fuzzing. All right. All right. So which kind of exception is most likely to be exploitable? All right, I'll quit at 25. All right, and that's the access violation, which suggests that some address has gone somewhere unexpected. That might be something awesome like the EIP that you control. It might also, and almost always when Ben fuzzed it, was just running off the end of a memory segment going too far. And that was not exploitable, and that's what all the ones we could find seemed to be. But anyway, that's life. That's the problem with fuzzing. You find a bunch of junk and then you can't exploit it. All right. Which technique makes it easiest to determine whether flaws are reachable? All right. I'll quit at 25. Of course, in general, dynamic analysis, fuzzing, means if it crashes, you have a DOS exploit. You know that the input actually reaches some vulnerable code. Static analysis is the one that suffers from finding a bunch of vulns that you cannot reach with input, so they are like of academic interest only. All right, and which one waits for the server to send a prompt? Quit at 25. All right. And that's read line, of course. Kind of obvious it will. All right, good enough. So I'll see we got the most of these right in a minute, but actually, since I got a little time, I want to show you as far as I've gotten on this staples attack, because it's a lot of fun. And for a while, I thought I was not going to be able to prove that the new version of it was vulnerable, but I figured out how to do it. So I think this is going to be a fun project. All right, it's only, all right. So what happened? I notified Staple about this in January. They got it automated. This is actually kind of interesting itself. If you contact Staples, there is an address in the app telling you where to send feedback. And when you send feedback, you get an automated response telling you, thank you, we will fix it in later releases. So they actually promised to fix it, and this is an automated response. I highly suspect no human ever saw my message at all. Because I asked them like a month later, so what are you doing? And they don't even answer me. So that's when I wait another 2 months and I say, well, these guys are dead in the water. And besides, it's more serious than I thought. Because the first time I went through, I missed some things, which I'm finding the second time. So the Staples app lets you have deals, but the other thing it lets you do is create an account, and you can store passwords in your account. Let me go back to this one. That's what I was, not only, so you create an account, the name and a password, then it logs you in, and then you have an opportunity to store passwords in your account. And I said, this is awesome. But the passwords are not stored on the phone. They're stored on Staples servers, and they're sent with HTTPS. So that's not terrible, but your password is stored on the phone, which is a pretty bad thing to do. And HTTPS.
Oh, HTTPS.
Yeah. So it's proper encryption and everything. So they send the credit cards up to the server in a secure way and don't store them on the phone, which is the right thing to do, but then they store your password on the phone, which is kind of nuts. That's like locking the vault and putting the key under the mat. So now they don't just store it in plain text though. If you look on the phone and search for the string password, you will find the encrypted password here, which is just a blob of base64 text. So that could be okay depending on how they've encrypted it, although I found...
Base64.
What's that?
It's just base64 encoded?
Well, it's not that bad.
Okay.
It could have been. That would have been awful. And of course, there are apps that do stuff like that. It's not that bad, but it's still pretty bad. And I found a nice article actually talking about this, where to put your password in an Android app. And they have the sense that the first thing is don't. You shouldn't store your password on the app, but they didn't put that in this article. But obviously, why do you store the password anyway? The only point is so the target or what Staples server knows who I am. So they should just store like a cookie, a random number on my phone that only they know. It shouldn't be my password because losing someone's password is far worse than letting them in your company's account because people reuse passwords. You should treat a password with some care, but they're totally not. So the worst thing is put in plain text. The next thing is encrypt it with a symmetric key, which is what Staples did. But there is an Android key store, and they show you the code. It's just a couple lines of Java. Just send it to the official key store for crying out loud. If you must save it, they provide a safe place to put it. Or, encrypt it with an asymmetric key that comes from a server or something so nobody can get at it. These are good ways to go. But they chose item number 2. And then the question is, if you're going to store it with a symmetric key, where do you store the key? And how do you get the key? And what they do is security through obscurity. They try to create the key from some algorithm that they think you're not going to figure out. And they're wrong about that because it's not very hard to figure it out. So the first thing, though, which I learned from the BERT product and the web application tool is how to detect security problems. So here I have some kind of encryption in base64 and I don't really know what it is. Well, the first thing to try is simple, obvious cryptography mistakes. They've already convinced me that they're pretty stupid because they shouldn't be doing this at all. And so how stupid are they? Well, like I say, there might just be base64. So I reverse it and it just turns into a bunch of garbled hex. So okay, it's not just base64, but the next thing you do is you make a password that is 32 identical letters. And then I had to add a few more because they have a thing where you have to have uppercase and lowercase and numbers or something. But the point is, if they're actually using some kind of electronic codebook encryption, then there'll be a block of text that's going to be either 8 bytes or 16 bytes. And when you have another duplicate 16 bytes, it will have the same result. So the question is, if they're using a sensible encryption mode like cipher block chaining, then it doesn't matter how many times you input identical input, the output will always be different because it adds a varying nonce to each one. So if I make a password with 32 identical characters in a row in it, and then encrypt that, I get an encrypted password that's much longer, and it doesn't appear to repeat. But that's because it's in base64 encoding, so all you have to do is reverse the base64, and it does repeat. 13, the first, so you have, this is using a block size of 16 characters. So the first 16 characters are here, the next 16 characters are here, and here's the 1, 2, 3A. Yeah.
And the reason it doesn't repeat in base64 is because of the odd number of...
Yeah, because base64 encodes at 6 bits at a time, right. and this is 16 bytes, which is not an integral multiple of 6. Right. So like half of this ended up in the first part, and a couple bits of it leaked over the next part.
But if you had chosen your A repeating 6 times...
That's right. If I had made it 6 times 16 A's,
right.
then you would see a longer string that repeated.
Right.
Yeah, exactly. So this shows me they made another mistake. So they used whatever encryption routine they're using. They are using it in electronic codebook mode, which is a bad thing. But still, that's not really that bad because I haven't found the key yet. So I tried to find the key, and I went on the device, and this actually, now when I first did it, I had to spend days grepping through the source code, looking for password, looking for key. But after I did that, it turned out to be extremely easy to have a logical path to get there. So here's the proof that repeating characters repeat in the encryption. So then you just open up the source code, unpack it, and you can read the Smalley. And so the first thing I did was, remember, the data up here has this thing called encrypted password. So that's something to look for. Find where that string appears in the source code. And that turns out to be very simple. So that code appears here, always in one routine. That thing appears only in this thing, Smalley app, staples, mobile, CFA, K, e.smalley. They are using the worthless ProGuard obfuscator, which changes about half of the names of the files to A, B, C, D, E, and does not change the names of the variables in the file very much, so it's sort of useless. It makes some idiot manager believe that you are resisting code reverse engineering when you are not. Anyway, so this contains the string encrypted password 4 times, and no other file contains that string at all. So that's obviously a place to look. So when you look at that, it is extremely simple. This is the method. Here's the username coming in. Here's the encrypted password. This calls some function called GU. Then it calls some function called M. And then it puts that string in the thing called shared preferences. And that's where I found it. I found it here in the shared preferences file. This is shared preferences, com.staples XML. So that is the routine that writes it into that file. So that's pretty awesome. And I didn't have to work very hard to find it. So in order to write it in the file, it starts with the password and it calls 2 functions to encrypt it, GU and M. So GU is just elsewhere in the same file. So if you look at GU, this is what builds the key. And all it does is interrogate your device for the brand, device, model, serial number, and the name of the app. And it sticks it all together in a long string. So that is pretty simple. And then if you go to the M function, it calls the B function. And if you look at the B function, it invokes AES in electronic codebook mode. And then it calls the capital M function to do something to it. And all the capital M function does is add extra salt to the start of it. So the glorious key, which is what I sent to Staples, by just analyzing your source code, even I did it with dynamic analysis, but you don't even have to do it with dynamic analysis. This is, there's, on my box, this was it. The entire thing was that. Let me just zoom it up so you can see it. That is it. Extra salt, generic VBox x86, Google Galaxy Nexus 4372 unknown was the serial ID of a JMotion emulator, and this is the name of the app, app.staples. It's just those words rammed together. Then you run it through SHA-1. Then you take the first 128 bits, use that for an AES key. You can just go to an online AES, and that's it. So, I'm almost done writing up the instructions. So when you do it here with Trojan code, it's kind of fun to see it go. Add code that'll put this in the log so you can see that string and see how it works. And now, what I just found out a couple hours ago playing with this, there are easy command line commands available in the console to get all those parameters, the model, the serial, and everything. So you can just go to ADB and get those strings. So what I'm going to do is have students go through this and turn in a screenshot, and then for extra credit, I'm going to give them encrypted stuff. And the task is to decrypt it, find my password, log into my account, and steal my credit card. I'm going to fake credit card number on the Staples servers and let people steal it. And the social engineering part of this is I would like to know how long it is before Staples does anything about this. Because I'm going to have them stealing credit card numbers from their servers for homework. And I think it's legal. Because I'm giving them permission to go in my account and steal my fake credit card, and if they come after me to get me fired and everything, it will create more drama and perhaps pressure them to fix it. It occurred to me someone might actually care if you point out that the end result of this is you can steal credit card numbers from people. They encourage you to put credit card numbers in the app, and they store them in this insecure fashion. So it's pretty gruesome. So we'll see if I can manage to get in some trouble this semester. No one's been yelling, screaming for my head for a while, and I feel neglected. So anyway, I'll have that all written up by like tomorrow or the next day. It'll be homework in the other class, but we'll see what happens of it. Anybody got any questions or anything? Well, I'm going to stop the recording and see you on the iClickers, and I'll go to the lab and help anybody that wants help there. This is 127 fuzz. Okay.